Hello, Mr. Betts here. So I want to take a look at a few different examples where we might apply these direct proportions and inverse proportions, and look at how we might set up a differential equation to model the situation. Right now, we're not worried about solving the differential equations. That's going to be something that we worry about later on in this unit. Right now, we just want to look at how we might set up equations that can model a situation. So in the first one here, we have a particle that's moving along a straight line. This is a pretty common calculus question. We have a particle moving along the x-axis, or sometimes they'll say like a squirrel running along a power line. So the squirrel really only has two directions to go. It can go forward or backwards. So the speed of this object is proportional to the square of the distance s it has traveled. I'm going to change speed and think of this in terms of velocity. Uh, and so the velocity is the rate of change of a particle's position. So velocity we can think of as a rate of change, and it's a rate of change of its position, which in this example is s. So s is changing at some rate. So this is the speed here, and it's inversely proportional. So that inverse proportion means that we're going to have some constant divided by the square of the distance it has traveled. So divided by s squared. Now, if you remember from my introduction video, an inverse proportion means that we have two quantities that multiply to get a constant. And we can rewrite this equation here as ds dt times s equals some constant. But for purposes of solving differential equations, typically we're going to want the derivative by itself. So usually when we have inverse proportion problems, we're going to set it up like this and take a constant divided by the quantity that it is inversely proportional to. In our example, second example here, this is actually called Newton's law of cooling, and it gives us a relationship between say the temperature in your living room versus the temperature change in your cup of coffee. So your coffee is going to cool to the temperature of the room. Hopefully, well, you could be drinking cold coffee, I guess. And this relationship here actually describes that mathematically. So the warming or cooling rate of a drink is proportional to, when it doesn't say direct or inverse proportion, it means direct. So that's something to keep in mind, that if it just says proportional, that is a direct proportion. So it's proportional to the difference between two things. So the ambient temperature in the room, so that's just room temperature, and the temperature of the drink. Okay, so let's start with the warming or cooling rate. Since it's a rate, we're going to use a derivative, and that's describing how fast the temperature of the drink is changing. Well, the temperature of the drink is T, so how fast T is changing is going to be dt dt. So d big T over d little t. So big T represents temperature, little t represents time. Now that's proportional to, so we're going to say equals K times. Now it's proportional to the difference. Remember, difference means subtract. So the difference between the ambient temperature and the temperature of the drink. So we get that. So this differential equation right here is actually a differential equation that will describe how fast your coffee or whatever hot drink, hot cocoa or whatever, cools and gets closer and closer to room temperature. This last example, we actually have two things going on here. So a patient in the hospital is getting an IV. They're getting drugs through the IV at a certain rate. So we know that they're getting medicine at a rate of 3 cubic centimeters per hour. But at the same time, their body is metabolizing that medicine at a rate that's proportional to the amount of the medicine in their bloodstream. Okay, so they're metabolizing or removing it at a rate proportional to the volume of medication in the bloodstream. So the rate of change of the amount of medicine in their bloodstream is actually going to be a difference of two things. So how fast the volume is changing is going to be dV dt, and that's going to be that's going to depend on two things. So one, we're just adding 3 cubic centimeters per hour. Okay, so if it were just dV dt equals 3, that means that it's just increasing by 3. So there's 3 cubic centimeters per hour being added to the bloodstream every hour. However, it's also we're also taking away some, and that is proportional to the amount of medication in the bloodstream. So it's proportional to V, so it's going to be K times V. So this relationship right here, this differential equation, is going to describe how fast the amount of medication in the bloodstream is changing. And like I said, we're adding medication and the body is metabolizing medication. And a lot of times in medical situations, they try to balance those two things. So they try to add medication at the same rate that the body metabolizes it so that we keep a constant amount of the medication in the bloodstream. Now, obviously, that depends on the treatment, what you're being treated for, and stuff like that. But it is something that is used to calculate how much medicine to give patients.